Hi, welcome to lesson 15D, the quotient rule. The goal of today's lesson is to differentiate the quotients of functions. It'll give us a nice easy way to differentiate as opposed to changing a quotient of functions into a product of functions. So as a quick review, a quotient is simply the division of one function by another. So 2x cubed minus 5x plus 1 is a function, and we're dividing by 4 minus 7x. That would give you an example of a quotient. 3x to the power 4 minus 2 over the square root of 3x plus 5 is also a quotient, as is this final example of quotient of functions there. So in yesterday's lesson, 15C, we learned how to differentiate a product of functions. And now we're going to learn how to differentiate the quotient of functions. Now on the Khan Academy, there is a video that Salman Khan does to show how to start with the product rule and derive the quotient rule after that. It's actually a very neat little video, neat little manipulation of the formula, and it's the link is available on the Canvas website. Okay, so the quotient rule states that if q of x is a function and that equals u of x divided by v of x, then q prime of x, or q dashed x, equals the derivative of the first function, u of x, multiplied by v of x, minus the function u of x multiplied by the derivative of v of x, all over v of x squared. Now, in the product rule, it doesn't really matter which group of, or which product of derivative and function comes first and which comes second, because you're adding. The fact that we're using the quotient rule and its subtraction, it makes a huge difference which one comes first. So you must do the derivative of the top multiplied by the bottom first, and then subtract the top multiplied by the derivative of the bottom, all over the bottom squared. Or if you wanted to look at it as y equals u over v, where u and v are functions, then we can say dy by dx is u prime v minus uv prime all over v squared, which is essentially the same thing as this form. Okay. Now the other little note that we have to be clear about is that the function on the denominator can never be 0. So v of x cannot be 0, or v in this case cannot be 0, because otherwise the function q of x, or the function y in this case, will be undefined. Okay, so we can't do that. Alright, so let's use the quotient rule to differentiate this function y equals 2x minus 1 over x plus 1. So what we can do is we can do some little side work over here. So we can say u of x equals 2x minus 1. Therefore u prime of x, or u dashed x, equals 2. And then v of x equals x plus 1. And v prime of x equals 1. Now we just have to put everything together, and so dy by dx equals the derivative of the top, which is 2 in this case, times the bottom, which is x plus 1, minus the top, 2x minus 1, multiplied by the derivative of the bottom, which is just 1. And that is all over the bottom squared. And we're not going to go through a whole lot of simplification. We'll just simplify a little bit here. So we'll just say 2x plus 1 minus 2x minus 1 okay, so technically you could expand this in, take off the brackets here, simplify the numerator. I would never expand the denominator, because we could use the denominator to find where there are zeros and vertical asymptotes, etc. So you would not want to expand this out, because that would make that little task much more difficult. Okay, moving along to the next example. We say u of x is x, u prime of x is 1, v of x is x squared plus 1 all squared. Now here's a place where we can employ the chain rule. So the derivative of the outside multiplied by the derivative of the inside, and then that we can simplify a bit and say 4x times x squared plus 1. And now we just put all the pieces together. So dy by dx equals the derivative of the top, which is 1, multiplied by the bottom, which is x squared plus 1 all squared, minus the top multiplied by the derivative of the bottom. Maybe we'll put this in square brackets, all over the bottom squared, which is x squared plus 1 squared squared. And then now we can just simplify that slightly. I'm not going to go through a whole lot of hassle here. I'll say x squared plus 1 all squared minus 4x squared times x squared plus 1 all over x squared plus 1 to the power of 4. And that'll be as far as we go. Okay, so now for this last example, we want to find the gradient of the tangent to this function at x equals 1. Okay, so why don't you give that a try actually. Could you please pause the video now, take the derivative using the quotient rule, substitute in x equals 1, and then see if you can find the gradient of the tangent, and then you can check back to this video to see how you've done. Okay, so now I'm going to say that u of x is 3x to the power of 4 minus 5x plus 2, and u prime of x equals 12x cubed minus 5. Now for v of x, I'm going to rewrite that as x minus 2 to the power 1/2. And now I'll take the derivative of that. V prime of x is 1/2 x to the negative 2 to the negative 1/2. Now I'll just put all the pieces together. So dy by dx, derivative of the top times the bottom minus the top multiplied by the derivative of the bottom, and here I'll put square brackets again, all over the bottom squared. And I'll just simplify a little bit. You can do a lot more simplification than I'm going to do right here. Well, a ton more, because I'm not really going to do anything. And which could make the subsequent substitution and evaluation of the gradient much easier. But I'll just kind of leave it as is here. All over x minus 2.